Hey guys, Dalton here from Home Advantage. This is a great example question because it actually uses all three types of our critical points. So it simply says find and classify the critical points of this function on, and it gives us an interval, okay? And it looks really simple, and it can be, but when you go through, if you go through it without considering all three types of critical points, you might just end up with a single point here and not getting the correct answer, okay? So let's just do a slight reminder. There's going to be a lot. This is probably the most jam-packed question I can think of for just thinking about what's going on and how we take derivatives and how we analyze them and second derivative tests and first derivative tests and all the fun stuff, okay? So just a reminder. There are three types of critical points. Now, you might be thinking, max, min, saddle point, or inflection point. Okay, those are 3 points. But I'm talking about the difference between a stationary point, okay? So this is where the derivative is actually zero, right? Which means when you take that derivative, you can set it equal to zero and you can find a point. You can use the second derivative test or the first derivative test to classify that point. But the two that people forget about are singular points and endpoints. So singular points is where the derivative is actually not defined. And this actually has to do with like limits and continuity factors and all kinds of fun stuff, but it's important, okay? And so you might even see it written as like, hey, this derivative like doesn't exist. Okay? It's not defined. Endpoints are a little bit more obvious, okay? The one thing I will say is that we actually only care about them on closed intervals. Okay. So like in our example that we're given, this square bracket, this actually means a closed integral. Or not integral, a closed interval, meaning that x equals 0, it actually exists and is part of this. If it hadn't been that and it had been a round bracket, that would have meant that the graph was actually starting ever so slightly after 0, meaning it's an open interval. Oh my goodness, I've got integrals on the brain. They're coming up next for you. So we want to look at all three of these types of function or types of critical points. So the stationary point one, that one is the simplest in some ways, right? We're going to take that derivative and we're going to set it equal to 0. So if I have a function that is 3 over 7 times x minus 1 to the 3 over 7, and I take the derivative, I always want to make sure that I'm indicating that I'm taking the derivative. You could also use a dy dx notation. It does not matter, but you don't want to just hit equals and continue on. The derivative of 3 over 7 times x is just 3 over 7, right? Because it's just a coefficient times x. And then for our next term here, it's actually going to be chain rule, even though the derivative of the inside is just going to be 1. So we're going to bring down that exponent of 3 over 7. We leave the inside alone, and we subtract 1 from our exponent there. The derivative of our inside, the derivative of x minus 1, is just 1. So our function here, minus 4 over 7, okay? And so we can set it equal to 0. And we can solve for our stationary point. I'm going to bring this entire term over to the other side. So it's going to change signs. This is a really like smart problem in the sense that we're going to get some nice numbers coming out of it. Okay. And so these are going to cancel, and I'm going to be left with x minus 1 to the negative 4 over 7 is equal to 1. One of the other reminders here is just about our exponent rules, okay? So if I have x to any exponent is equal to some other number, and I want to get rid of that exponent, I am going to actually raise both sides to just the inverse of that exponent. Because remember, if we do the same thing to the left side and the right side, we get the same number. And if we take something that has an exponent and we raise the whole thing to another exponent, we're actually multiplying those exponents together. And so we end up with a over a, aka it's just 1. So it goes away. You don't have to write out all of this work. I'm just reminding you that if I have a messy exponent, like this negative 4 over 7, to get rid of it, I am actually just taking the other side and raising it to the inverse, 1 over that. So that would just be 7 over 4 in this case. Now, 1 to any exponent is always just going to be 1. So this leaves us with a critical point happening at x equals 2. Okay. I like to make sure I know what the whole point is. So I go back to that original function of 3 over 7x minus x minus 1 to the 3 over 7. And I want to figure out what that y value is when I plug in my point of 2. It's going to give me 6 over 7 minus 1. So negative 1, 7. So we have some kind of critical point. At 2 and negative 1, 7. Okay. We can use the second derivative test here to figure out if that's a max or a min, right? That first derivative was 3 over 7 minus 3 over 7, x minus 1 to the negative 4 over 7. And so when we take that derivative again, right, 3 over 7 has no x, so it goes away. This negative 4 over 7 is going to come down and get multiplied by our coefficient of negative 3 over 7. Oh, that's 4. And subtract 1 from that exponent. The derivative of the inside for our chain rule is just 1 there. And so what we end up with is going to be 12, 7 times 7 is 49, x minus 1 to the negative 11 over 7 there, okay? And so to actually test our point, we're just going to plug in x equals 2. And we will get just 12 over 49. We don't actually care about the value. We care that it is a positive number. Positive, we think smiley face. That means we have a minimum. So that means since our second derivative is positive, we have a minimum at x equals 2, where y equals that negative 1, 7. And this is where most students would, they'd be like, look, there was one critical point and I figured out what it was. Whenever there's just a single critical point, that would actually mean that it's a global minimum. And they would say, hey, this is a global minimum, and they would move on. And that's not going to be right here, okay? So We did just figure out the stationary point, but now I also want to look at singular points. And singular points do not show up on every question, nor do endpoints. That's why they get missed when they do show up. Okay. So singular points are where the derivative doesn't exist, but the function does. Honestly, around singular points, there's a lot of interesting and cool math. I am giving you the COM 161 rundown here, okay? If you're a person from the random internet who has found this video and is watching it and you're like, this is not good math. Well, nah, we're doing first year business math here. We're just trying to get an A plus on our final. We don't really need to be mathematicians. That being said, I do have a degree in mathematics. Anyways, so singular points are when the derivative doesn't exist. And there's a few different ways that this can happen, but the main thing that we're going to be looking for in the context of this class is when we have x's in the denominator, and it's possible for that denominator to be 0, because the whole rule is that we can't divide by 0. So we're only ever worried about this. We're going to check for singular points when we have variables in the denominator. Okay. And so of the derivative. Okay. So when we look at our derivative, it was this 3 over 7 minus 3 over 7 x minus 1 to the negative 4 over 7. And I think this is what kind of messes people up, because you can leave it like this and you're like, there's no denominator. Oh, but there is, because there's that negative exponent, right? We can rewrite this function by putting this x minus 1 term with the 4 over 7 in the denominator. And so this means that this whole function, that the derivative will be undefined. Okay, if you try to put in your calculator will freak out. When 7x minus 1 to the 4 over 7 is equal to 0, right? If you try to put into your calculator 3 over 7 minus 3 over 0, it's going to be like, well, I can't do that. And it can't do that because it doesn't exist, okay? And so what value, so our singular point is going to be, singular point is the x value that makes the denominator 0. Now you might look at that and be like, oh, that means it's x equals 1. If you don't, just take that denominator and set it equal to 0 and solve for x, right? I divide both sides by 7. Remember, when we're getting rid of weird exponents, we just raise the other side to the inverse. 0 to anything is 0. So I end up with this point, a critical point of x equals 1. Because we're doing, again, far more interesting things than just stationary points, I really want to make sure that I understand what's happening in my graph. So I'm going to go back to my original function, and I'm going to plug in 1. Yep. And so if I do that, I get 3 over 7 And so this means that we have a singular point at 1 and 3 over 7. Is that a max? Is that a min? I don't know. But also, I can't plug it into the second derivative. If I try to plug this into the second derivative test, or singular points fail. Okay. So if I took that second derivative that we found before, right? That 12 over 49, 1 minus, or so, well, let's just put the formula x minus 1 to the negative 11 over 7. You try to plug in 1. You are going to have 0 to a negative exponent, which is undefined. So it's like, I don't know what to do with those singular points. Okay, singular points, we really do have to think about what the shape of the graph is. Okay. The other thing that we had here was an endpoint. Now, that endpoint is because they gave us the interval of 0 up to positive infinity, okay, which means our graph starts at 0. Again, this is a closed interval, meaning the graph, right, that x equals 0 exists, and it's the beginning of our graph. So that means that we have a critical point at x equals 0. We probably want to know what value that corresponds to. Minus. So we're going to get a negative 1 there. And so we have a critical point at 0, negative 1. Okay. So to recap here, we have one of each type of critical points, right? We have a stationary point at, oh, not 0, at 2 and negative 1/7. And we figured out that that is a minimum of some kind. We have a singular point at 1 and 3/7, and we have our endpoint at 0 and negative 1. So the stationary and the singular points are the only places in which we can change direction, okay? So you could use a first derivative test to probably figure out what's going on here. This graph starts at 0, 1, 2. It's just going to continue on, okay? We're just going to put in our points. So I'm going to have this negative 1 down here. This is my endpoint, right? At negative 1, 0. I had a singular point at 1 and 3/7. So 3/7 is something less than 1. I'm just going to put it up here because it's positive. Ah, no, my nice line. So there is a point here. What is it? And then we also had our point at 2 and negative 1/7. So negative 1/7 is going to be something less than 1 there, okay? And so we know that this one was a minimum, okay? And we also know that these dots are the only places things can change direction. So even if you drew this graph terribly and you were like, inflection, you should probably get some idea. Okay. This is a terrible graph because I just added a bunch of points. But the point here is that if I know that this third dot on my graph is a minimum, that means that leaving that, they have to increase. So here we're going to go up to infinity, right? Because the graph goes off to infinity. In the other direction, I can only go to this point here. My endpoint and that 1, I can't change direction, right? If I was changing direction, that would mean that there would be more stationary points somewhere, right? Which means I'm going directly from that -1 to that 1 in some kind of increase, right? Singular points are very often these kind of jarring ups or down points. The derivative doesn't exist because they're converging in different directions, like they don't continue on. Again, that's getting into like real math stuff that we don't need to know, okay? And so when we look at this, to classify each of our points here, this endpoint at -1 is actually the lowest point on our graph. So this is going to be a global minimum. When we look at what's happening at x equals 1, the stationary point, that is a maximum, but it is only a local, or sometimes we call it a relative, it doesn't matter, maximum. Okay. And the minimum that we found, it is a minimum, but it's not the lowest point of the whole graph. So this is again only a local or relative minimum there. So when we think about these 3 points, our stationary point ended up being a local minimum. Our singular point was a local maximum. Our endpoint was a global minimum. And in this graph, there is no global maximum because our graph is actually just continuing up for infinity there. Okay. So, big doozy of a question in all honesty, but a great example of all 3 types of critical points in one.